This segment, let's go ahead and discuss significant figures, or as you've probably heard, they're more likely called Sig Figs. This is something that's going to come up throughout your scientific career as long as you're doing chemistry and physics or anything of that nature. So you're going to want to go ahead and do your best to get a handle on understanding of Sig Figs. The beautiful part about this is that there are actually some rules and very few exceptions, so that if you do it with practice over and over, it should become second nature for you. So we do significant figures because we need to account for the degree of uncertainty in a final numerical result. So if you're in a laboratory and you've got a bunch of measurements and you want to add them together to get a final result, you want to make sure that your final result is as accurate as your initial measurements were. So let's start with the rules. The first rule applies to non-zero integers. So non-zero integers always count as Sig Figs. So if I have a number 1, 2, 3, 4, all four of those numbers will be significant figures. Secondly, zeros. Zeros are going to be the largest source of complication. So there are three classes of zeros when it comes to counting Sig Figs. The first applies to leading zeros. So those are the zeros that precede non-zero digits. And those guys never count as Sig Figs. They just indicate the position of the decimal point. So for instance, 0.00123, these zeros are all leading zeros. They never count as significant figures. So this number only has 3 significant figures. So only the non-zero integers count. The second are captive zeros. Those are the zeros that fall in between non-zero digits, and those guys always count as Sig Figs. For instance, if you had the number 1.0012, you're going to have 5 significant figures. So all of these numbers are significant because these zeros are captivated basically by the non-zero integers on either end. The third class of zeros are trailing zeros. So these guys are zeros at the end of the number, and they're significant only if the number is written with a decimal point. So for instance, if you have 1,000 just written 1000, the only number that's significant here is the non-zero integer 1. However, if it's written 1000 decimal place, then you have 4 significant figures. So I guarantee that the zeros, whether they be on the right-hand side or the left-hand side, are going to be 2 of your pitfalls. So it's really important to understand how the zeros on the front end work and how the zeros on the back end worked. Last but not least, for Sig Figs, we have exact numbers. So these are numbers that were determined by counting and not by doing an experimental procedure. For instance, if you had 6 apples or 10 pens or something of that nature, those guys are just the number that they are. So they're assumed to have an unlimited number of significant figures. These numbers can also arise from definitions. For instance, if you're doing a calculation and you're saying that 1 inch is equal to 2.54 centimeters. It's your significant figure value, your final result, will not be limited by either of those values. And it also applies to scientific notation. So if you've got 100 written 100, that's got 3 Sig Figs. If you wrote 100 in scientific notation, which would be 1.00 times 10 squared, that also has 3 significant figures because these zeros are important. So chances are you're going to have to actually do significant figures in some calculations. So let's discuss how it applies to multiplication and division and addition and subtraction. So for multiplication and division, the number of Sig Figs in the result is the same number as that in the measurement with the smallest number of Sig Figs. So we call the number with the smallest number of Sig Figs basically your limiting term. Okay, so you're limited by how accurate your smallest measurement is. So for instance, here I've written 5.16 times 1.3. So you're going to be limited by the 2 Sig Figs here in 1.3. So the answer as a result of this multiplication is 6.708. So something to note here too is that you want to write out all the digits first before you round. Otherwise, you're not going to be as accurate in your final measurement. So if we're dividing, let's say we have 5.168 divided by 1.43. So 1.43 is going to be our limiting term, meaning we can only have 3 significant figures in our final answer. So the result of this division is 3.61398,601, all the numbers that showed up on my calculator. And then I will round that down to 3 Sig Figs, which would be 3.61. Again, I'm limited by my limiting term, which had 3 sig figs. So let's lastly do addition and subtraction. So it's a little bit different, as the limiting term here is the one with the smallest number of decimal places. So if I had 16.15, 14.1, and 1.06, and I'm adding them together, I'm going to be limited by 14.1 because it only has one decimal place. So then my answer on my calculator would become 31.266, and I would round that to 31.3 because, again, I'm limited in my answer by the one decimal place. Same thing for subtraction. If I had 16.15 subtracted by, and I'm subtracting 0.4, my limiting term is going to be 0.4. Again, I'm limited to one decimal place in my answer. So my answer on the calculator would be 15.75, which I would round to 15.8, having one decimal place. And that's significant figures.